Hi everyone, welcome back. So today we're going to be talking about binomial distributions. This is a very specific type of probability distribution that I want to talk about today. So basically, a binomial distribution is very black and white. It only has two outcomes, a success or failure. And so we have to, in each question, we have to define what is a success and what outcome is a failure. So an experiment has a probability of success, so P, and a probability of failure, which is Q. Now, quick note here that because there's only two possible outcomes, success or failure, that means probability P is equal to 1 minus Q, right? Or vice versa, we could look at it as Q is equal to 1 minus P, right? So if we know one of Q or P, we know the other one as well, right? Because we either succeeded or we failed. And that's pretty much it. There's not really a third option. The experiment can be repeated, and each trial has the same probability distribution. And then in repeating the trials, the probability of the frequency of a single event can be found. So, let's translate that a little bit to English. Basically, what it's saying is that we can do the same thing over and over. So we could roll a die over and over and over again, and we could define even numbers as those are successes and odd numbers as failures, and we can find what's the probability of if we roll the die 5 times that we'll get exactly 2 successes, for example, or exactly 1 success, or exactly all 5 successes, or anything like that would be an example. So let's talk about the binomial distribution equation, and I also want to get into like why is that the equation of all equations. So here it's the probability of x being anything, right? We're not sure what it is in this case, just this is the general case, is equal to ncx times p of x, t to the power of x, times q to the power of n minus x. So basically what this is saying is this probability here, p, we're going to take it to the power of however many successes we're getting, right? So let's say, for example, the probability of success is a 6, right? Maybe a success is rolling a 1 on a die. Let's say that's a success. And we want to get 3 of those. Well, the probability of getting 3 in a row would be 1/6 the power of 3, right? So p would be 1/6, and x would be to the power of 3, right? Now let's say it's exactly 3 times, but we're rolling the dice 5 times. Well, in that case, we would need the total number 5 minus 3, right? Minus the number of successes is going to be the number of failures. So that means we need 5 out of 6, right? Because all the other 5 numbers are failures to the power of 2, right? And so if we kind of look at it that way, it's like, oh, it makes sense. We're saying we need to have 3 successes, right? 3 things that have a 1 in 6 probability, 3 1s on our dice, and we also need to have 2 other numbers. So um, 2 numbers that are not 1, right? And there's a 5 in 6 chance of getting something that's not a 1. So there we have it. Now you might wonder, well, then why do we need this? And it's because the order doesn't matter here. And so we need to multiply this by the total number of orders, right? The total number of ways we could possibly order these, right? And the reason being is because if we just stop here and say, oh, this is the probability, it's 1/6 the power of 3 times 5/6 squared, this is the probability of one specific order, right? This is the probability of the first 3 are successes and then the next 2 are failures. And obviously that's going to be a smaller probability than just the probability that we get 3 successes somewhere, 3/1/6 probabilities somewhere in our experiment, which is really what this is asking. They're not asking what's the probability that we get this many successes first and then the rest failures. No, it's asking what's the probability of just at some point in the experiment getting exactly 3 successes, right? Or however many successes or failures we're wanting to look for. And so what this takes into account is it takes into account the total number of combinations of ways that we can arrange this, right? It says let's take n, which in this case is 5, and let's choose x, which we said was 3, right? We're going to take all 5 of these outcomes and then choose three of the spaces, right? Three of the spaces, in sequential order 1, 2, 3, 4, 5. Choose three of those spaces in which to put those successes. We have five total, you know, total trials. We need to choose three of those trials and figure out how many ways are there to choose exactly three of those trials to put our successes in. And then the failures just go in the other two spots, whatever they happen to be. So there's actually only one space to put the failures after we've already put the successes into those trials. And so that's why it's very crucial to do this. Otherwise, we will get the wrong answer. We will end up with the probability of one specific order when we actually don't care what order we get the successes and failures, as long as we get the correct number of successes and the correct number of failures overall in the experiment. Okay, so that's why this works. And I think that's really key to understand, well, why does this work? Because maybe on a test, you might forget, oh, what's the equation? Well, you'll be able to, pull it out of your head basically and get it back if you understand why it is the way it is, right? If it makes sense, why is this the binomial distribution? Then they have the expected value, right? What's the expected number of successes you're likely to get? Well, that's going to be n, the total number of trials, times the probability of one success, right? So times p. And this makes sense as well if we think about it of, okay, here's the probability of getting one success. We're going to multiply that by our total number of trials, right? If it's a half, right? If probability is a half, and we're doing 6 trials, then 6 times a half, well, that's 3, right? We're expecting, on average to get that 3 of those 6 trials will be a success, right? That half of those trials will be a success, right? What if the probability of a success is only a tenth? Well, then we're only expecting 1 in 10 of those total trials to actually be successes, right? So if there's 100 trials, we're only really expecting 10 successes, right? Which makes sense with taking the number of total trials times the probability that any one of those trials, that each trial is going to be a success. So that's a way to think of that one too. I think it's important also to understand how the expected value is measured and, well, why is it n times p in this situation? Why isn't it something else? And that's why. Okay, so now that we kind of got the terminology out of the way and hopefully have some understanding as to why the equation is what it is, I want to move on to doing an example here. So this example says, a spinner is divided in 5 equal sections labeled 1, 2, 3, 4, and 5, and is spun 40 times. Okay, so I'm actually going to draw a picture for this. Here's my spinner. Actually, let's draw a nicer spinner. There we go, that's a little bit better. There we go. So this spinner is spun 40 times. We do spin, 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 all the way till we get up to doing that 40 times. And we're going to record what numbers we got when we spun. So the first question is, what is the number of times that a 2 is expected to be spun? So in this case, we're going to define a 2 as a success, right? Probability of one success, 1, 2. Well, what's the probability of 1, 2? 1 in 5, right? The probability of spinning and getting a 2 is 1 in 5, right? Or 0.2, whichever you'd prefer. And the total number of times we're going to do this experiment is 40. And we're expecting that 1 in 5 times out of those 40, we're going to end up with a success. We're going to end up with a 2. And so the expected value is n times p, as stated earlier, which is going to be 40 times 0.2, which is 8, right? Which makes sense. We're expecting to get each number, including 2, about 8 times if we spin it 40 times. Now that's not to say that every time we do this 40 times, we'll get exactly 8 of each number, But that's what we're expecting because all 5 of these outcomes of getting 1, 2, 3, 4, or 5 are equally likely. There's a 1 in 5 chance for each, so we might get slightly higher than 8 in actuality or slightly less than 8 in actuality. But what are we expecting? What on average, if we did this experiment, millions of times, we spun this 40 times for each experiment, and then we did that, we replicated it, it's going to get closer and closer to that expected value, closer and closer to 8, right? So on average, on the average 40 times spinning, experiment, we're going to have 8 of those 40 times rolling a 2, spinning a 2. The next one asks, what is the probability of spinning a 2 6 times? Okay, so 6 times out of the 40. Let's think about that. So the probability is the same. It's going to be 0.2, right? Because probability is a probability of one success. So of spinning a 2 if we spin it once. Now, what's the number of times we're going to do our trials? 40 times. We're going to spin 40 times. How many successes are we measuring the probability of? 6, right? X is going to be 6 because we are wanting to know the probability of 6 twos, of 6 successes. And then lastly, what is Q? What is the probability of a failure? Well, it's going to be 0.8, right? It's going to be 1 minus P, right? So 1 minus 0.2 will give us 0.8. So those other 4 and 5 times, or that other 80% of the time, we're going to fail. We're going to get some number that is not 2, and only 2 is a success in our eyes. So let's do it. Let's plug that in. So P of X is equal to 6 is going to equal 40 choose X, which is 6, 40 choose 6, times 0.2 to the power of 6, right? Because 0.2 is the probability of spinning a 2, and we need that to happen 6 times, right? We need that 0.2 chance, right? That 20% chance outcome to happen 6 times for 6 successes. We also need, for the opposite outcome, Q, of spinning something that is not a 2, to happen 34 times, right? Because total we're spinning 50 times or 40 times. So 6 plus 34 is the total 40. So we've accounted for all 40 times in our experiment, which is good. Now I'm going to simplify this. So to simplify this, the 40 choose 6, you're going to go to your calculator, find the NCR button, the combinations button, and punch in 40 and then NCR 6 equals, and you should get 3838380. And then for 0.2 to the power of 6, that's going to be 0.000064. And then for 0.8 to the power of 34, that is going to be 0.0005, like that. And then if we multiply all those out, we get 0.12 approximately, like that. And there we have it. So therefore, the probability of spinning 2 exactly 6 times is about 12%. So probably not going to happen. However, it's not so far from that expected value that it can't happen or something, or is super, super unlikely to happen. If we do this experiment enough times, eventually we will hit that 12%, that 12% will hit, right? That 12% chance thing will hit, and we will end up spinning 2 exactly 6 times in a 40 trial experiment. Good. The next one says, what is the probability of spinning 2 4 times? Now, let's get something straight first of all. Even though this is possible, this is further away from the expected value than the last one we did, where we were spinning for a 2 6 times. And so this one is going to be a smaller probability. So if we get a larger probability here, then we're in trouble because we are expecting a smaller probability here since this is further away from our expected value. And so although, yes, this will eventually happen too, eventually if we do enough trials of 40 spins, experiments, eventually we will get 2 exactly 4 times, but it's going to take us longer than it would if we're just searching for, spinning a 2 exactly 6 times. But with that out of the way, let's do it. So in this case, all of our given values are the same except for x. X is the only one that is different, right? Because in the previous one, they asked about 6 times. This time they asked about probability of this happening 4 times, right? So x is going to be 4 here. So p of x is equaling 4. Probability of x being 4 successes is going to be 40, choose 4 this time. This time we're just choosing 4 places out of our 40 places, right? Our trial numbers, 40 out of our 4 out of our 40 trial numbers to be the ones that are the successes, and then the failures will fill in the rest of the 40 trials. And then 0.2 to the power of 4, right? This time we just need 4 successes. So for the thing that that occurs only 20% of the time, we need that thing to occur 4 times. And we need the other thing, right, the failure that has a 80% chance of happening, we need that to occur the other 36 times. So then we'll solve the same way as before. So let's just plug these things into our calculator and we'll get the answer we're looking for. And our answer is 0.047, right? So this time, instead of a 12% chance, there's only a 4.7% chance, which is good, right? That's about what we were expecting. We figured that if our expected value was, we're expecting to get 8 twos, if to only get 4 isn't that likely to happen. It's certainly less likely to happen than in our previous example where we were spinning it and getting 6 or 2 6 times. So there we have it. All right. So let's do another example here. In this example, the probability of a success versus failure was not actually the same, even though this is a uniform distribution overall, because the probability of each outcome is actually equal. In this case, we would consider it a binomial distribution because we are expressing that 2 is a success and everything else is lumped into the same category, right? So whether we get 1, 3, 4, or 5, we don't actually care. All we're looking at in this case is 2 or non-2. So I'm actually going to label it that way. I'm going to say yes. So I'm going to label this in green, the 2, because that is our success. And everything else is a failure, right? There's no distinction in our experiment specifically that we're doing now. There's no distinction between 1, 5, 4, and 3, because as far as we are concerned, they are all failures. So we don't care which number it is unless it's 2. Everything else fails us. Okay, so that's something I wanted to point out because I'm sure I'll get lots of questions about, well, didn't we just say this was a uniform distribution? And we did when we were actually considering every different outcome as a different outcome. But in this case, we're defining it at our outcomes of did we get a 2, yes or no? And in that situation, it would be binomial because getting a 2 is not equally likely to happen as not getting a 2 is, right? Because we're lumping 4 other categories that we would have in the uniform distribution. We're lumping them together and saying it's all one big category that's 4 out of 5, that has a 4 out of 5 probability of occurring. Good. All right, so let's do another example here. Actually, 2 more examples, it looks like. Here it says the probability of the New York Yankees winning each game during the season is 60%. What is the number of wins expected during a 20-game preseason? Okay, so expected number, right? Number of wins expected. That means they want the expected value, which as we know is going to be n times p. Now, n is the total number of games, which is 20 games. That's what they told us, 20-game preseason. And p is the probability of one success. Well, the probability of the Yankees winning, that's clearly a success, right? That, assuming you're a New York Yankees fan, that is a success. But regardless, that's what we're going to define as the success today, that a success means the New York Yankees won. We're rooting for their team today. So 60%. That is the same as 0.6. So if we plug those numbers in, that we're going to do this 20 times. There's 20 games in the preseason, and that each thing is going to, we're going to win about 60% of the time, then we're going to end up with 12. So we should expect about 12 wins out of 20 for this season. So we're expecting to win about 60% of the time and to lose the other 40% of the time. Good. The next one asks, what is the probability of the Yankees winning 10 games? Okay. So the probability of the Yankees winning exactly 10 games is equal to, well, going back to this equation over here is what we'll use. So we need to find out what n equals, p equals, q equals, and x equals. So x we already filled in. We said x is 10 games because that's what the question asked. They wanted to know what is the probability of winning exactly 10 games. N is 20. We already know that from the last question. And P is 0.6. Now Q, remember, is just 1 minus P, right? It's just going to be 1 minus 0.6 in this case, which is 0.4, right? Because binomial, it's very black and white, right? If we don't win, that means we lose, right? We're going to act as though there's no such thing as tying, or I'm actually not sure which sport this even is. Maybe it isn't possible to even do a tie in real life either. I don't really know much about sports, but anyway, we're going to pretend that tying, regardless of whether it is or isn't an option in real life, we're going to imagine it is not an option, that either we win or we lose, and those are the only two categories, because if that wasn't the case, then it wouldn't really be a binomial distribution. There'd be three categories, and that would be something else that we'll probably learn later. Good. Okay, so let's plug in those numbers. So it's 20, choose 10, right? And then we need 10 wins. And then that means we also need 10 losses, right? To fill in those other 10 games that we didn't win. If we plug this in our calculator, we'll get 184, 756, 0.00. 0.0001, and we're going to end up getting 0.116. So about 11.6% chance that the Yankees will win 10 games. So not impossible, but not that likely, right? It's not even our expected value. And to be clear, even if we did, find the probability that the expected value would happen, even that wouldn't happen 100% of the time. It would just happen more of the time than any other individual value we could possibly get, right? Good. All right, so there's about an 11.6% chance that the Yankees will win exactly 10 games. The next one asks, what is the probability of the Yankees winning exactly 15 games? Well, this one right off the bat, we know this is going to be a smaller probability than the probability we just calculated, because the expected number of games to win during this preseason is 12, right? And 12 is only 2 away from 10, but it's 3 away from 15, right? And so we're expecting a number slightly lower or we're expecting a probability rather that's slightly lower than the last one we just calculated. Now, N, P, and Q are all the same as before, so I'm just going to copy those from my last question. And then X is going to be 15 instead of 10. That's the difference here, because we want to know the probability of the Yankees winning exactly 15 games rather than exactly 10 games. Like that. And that's going to come out to 0.075, right? So there's now only about a 7.5% chance of them winning 15 games, which makes sense because that is a little bit lower than the 11.6% that we got previously when we had a number of games we were calculating for that was closer to that expected value. Good. All right, let's do one more example. Looks like this is a two-parter. It says a container holds 18 colored balls, 5 of which are red. 5 of which are gold, 6 red, and 7 gray. A ball is chosen from the container and then replaced and repeated 20 times. So basically, this is with replacement probability, right? We take out a marble and then we put it back. then we take out another marble, we record the color, we put it back. And so it's not as though as we take out marbles, the probabilities change. The probability of drawing a red, a gold, or a gray are always the same regardless which trial we're on, because after we take the marble, we just toss it back in. We put it back. Good. So the first one asks, what is the number of times red is chosen? Now, actually, we don't actually know, right? We don't actually know what number of times red is chosen, so I think this is a typo. I'm going to change the question to expected. What is the expected number of times red is chosen? Because the correct answer for what is the number of times red is chosen is it varies, right? It could be, anywhere from 0 to 6, technically, right? We don't know how many times red is chosen, right? Or sorry, it could be anything from 1 to 20 times rather. No, I think I said 1 to 6, but no, it should be 1 to 20 times. So we don't actually know, right? However, what we can tell you is what's the expected number. How many times of doing this, of choosing these, of choosing a ball 20 times then putting it back, do we expect to get a red? Okay. So what's the probability of one success, of one red being selected in one trial? Well, we have 18 balls total and 6 are red, so I'm going to say it's 6 over 18 or 1/3. And the number of trials is 20. We're going to, 20 times draw a ball and then pop it back in. Okay, so expected value is equal to n times p, which is equal to 1/3 times 20, which is equal to about 6.67. And that is rounded, by the way. That is a decimal approximation there. Good. So that means we expect that red will be chosen about 6 2/3 times. So, between 6 and 7 times. So the most likely occurrence would be we would draw it 7 times, followed by 6, and then so on, depending how far we get away from that. Okay. The next one asks, what is the probability of a red to be chosen less than 3 times? So what does that mean? That means the red would have to be chosen either exactly 0 times, exactly once, or exactly twice, right? So what do we know? We know that the probability of a win is a third, right? A third of the times we're going to pull out a red. Q is going to be 2/3, and n is going to be 20. And we need to find what is the probability that x is 0, right? That we don't draw a red ever. And we need to add that to the probability that we draw a red exactly once. And we need to add that to the probability that we're going to draw a red exactly twice. And notice it says less than 3 times, not less than or equal to 3 times. So we don't need to calculate the probability of exactly 3. We only need probability of that it's less than 3. So 0, 1, or 2 would be less than 3. Good. All right, so let's plug that in. Here we have 20, choose 0. Here we have 20, choose 1. And here we have 20, choose 2. And then here we have 0.33, or actually let's just be consistent and say a third. We have no wins, so no times does this happen. Here we have 1 win, and here we have 2 wins. And then that means if we have 0 wins, that means that we have all losses. So we must have full losses of 20. Here we must have 19 losses. And here we must have 18 losses. So if we punch those numbers in a calculator, we're going to get 0.00033. Over here, we'll get 0.0033. And here we're going to get 0.01463. So the probability that x is less than 3, right, that we get less than 3 wins, is 0.00033 plus 0.0033 plus 0.01463, which is going to be equal to 0.01826. And you might be thinking, oh, but that's less than 2%. That's a very, very low probability, and this was 3 categories. How did that happen? Well, I understand that this is 3 categories, and earlier, we're expecting more than this. Other times we've got higher probabilities for multiple categories. However, these numbers are quite far from our expected value. Our expected value is to get 6.67, right? So our most likely number is going to be 7 that we'll get. And we're calculating the probability that we'll get less than 3. So even though these are 3 categories and we're adding them all up, these are 3 very unlikely categories. It's very unlikely that I'm going to, pull 20 times, pull a ball out of this container and not once get, get a red. It's also very unlikely that I'll only get one exactly once. And it's also still, a little more likely than the other 2 examples, but it's still pretty unlikely that I'll only get it twice. If I'm pulling it out 20 times and every time that I pull out a ball, you know, I get 1 in 3 times that I do that, I get a red one, right? So even though it's 3 different scenarios, they're all extremely unlikely to actually happen, right? And so that's why, right? That's why this is such a small percentage, even though we're adding up 3 different categories, because all 3 of them are just very unlikely to happen. They're probably not really happening. Good. Now, any of them could happen, but I mean, any one of them happening, even if we lump those 3 together in a group, it's still less than 2%. So we'd have to do this experiment a whole lot of times for this to happen, for us to actually choose a red ball less than 3 times. Good. All right, well, that is it for binomial distributions. Next time, we're going to talk about geometric distributions, which are, relatively similar to this, in my opinion. So we will see everyone next day for that. Have a good rest of your day, and bye for now, everyone.